Our high-level problem statement is accurately estimating the rigid pose of a moving object with inherent symmetries from low-quality 3D sensor data. The challenges of symmetric ambiguity and limited detail visibility in the acquired data compound to create challenging pose ambiguities. The specific problem that motivates us in this paper is estimating the fetal head pose from fast MRI volumes called navigators, acquired rapidly for a real-time clinical application, which will be discussed later. Because navigators are fast acquisitions, they contain all kinds of imaging artifacts that mask anatomical details otherwise necessary for disambiguating pose. Also, fetal heads display approximate left-right symmetry, especially in low-resolution images where any asymmetric cues are hard to see. Because there isn't sufficient navigator data available, any learning-based pose estimation method also needs to be trained on larger datasets of higher quality volumes without the same kinds of artifacts, introducing a challenging domain gap. Existing methods struggle on these fast navigator volumes because they rely on being able to see details to disambiguate pose. This includes key point detection, rigid registration by aligning image intensity distributions, and directly regressing pose with standard CNNs. So we had to rethink traditional approaches to pose estimation to better handle these challenges. In our approach, we first segment the head from the volume and use the mask center to estimate translation. We train a second network to estimate rotation by predicting three orthonormal directions of the head frame relative to the scanner coordinate system. Prior work shows that how the network parametrizes rotation affects the stability and robustness of the learned pose regressor. Our key innovation is that we construct our rotation network architecture to jointly account for two inherent symmetries of the problem. First, the approximate left-right symmetry of the head, and second, the rotation equivariance of an object's rigid pose. Our approach is the first method to jointly model equivariance and object symmetry by construction. So how do we do this? The theory behind the development of equivariant networks supports operation on tensor fields defined over 3D Euclidean space. This formulation enables us to formulate the output rotation as three vector quantities that rotate in an equivariant manner with the object relative to the image. Recall that we want our rotation parametrization to be invariant under the object symmetry group, which for our problem means invariance under left-right reflections. But only vectors orthogonal to the left-right axis satisfy this condition. If a vector is completely parallel to the left-right axis, then left-right reflection is equivalent to the inversion operation. Here we introduce the concept of pseudovectors, which are similar to vectors in that both are rank 1 tensors that transform in the same manner under proper rotations. The difference is that while vectors undergo a sign change under inversions, pseudovectors are invariant under inversion. So if you are unfamiliar with the concept of pseudovectors, you can imagine them as double-headed vectors because one direction is equivalent to the opposite or inverted direction. So because vectors parallel to the left-right axis are inverted by the object symmetry group, pseudovectors parallel to the left-right axis are invariant under the object symmetry group. Here's one example navigator with particularly high pose ambiguity. The eyes and other details are hard to see, and the brain looks almost like a sphere. The red and green lines closely match in all alignments, which all seem visually plausible, but one can tell from examining the surrounding tissue that the pose predicted by the baselines is completely incorrect, while E3 pose is able to correctly recover the true pose. So can we use E3 pose to solve an important clinical problem? Yes. We use the estimated fetal head pose from navigators to adaptively adjust the imaging plane of higher quality MRI slices that are acquired for radiological assessment. Compared to the current standard of motion blind acquisition on the left, our method is able to stabilize the fetal head motion in the acquired slices, even as the baby undergoes large motion in the uterus, leading to better quality fetal imaging. More details about the clinical problem and the deployment of our method can be found on our project page. Thanks for listening, and feel free to check out our media.